Okay, Assalamu alaikum. Today we will discuss in this chapter about virtual memory. Okay, we have already discussed in the previous chapter main memory management different schemes which are used in computer system, and all of these schemes or method have the same goal, that is what, to keep more than one processes in memory at the same time so that we can achieve multi-programming. But all of these schemes require that your entire process should be in main memory before we can start it to execute. But when we are talking about virtual memory is a technique that allow the execution of a process that are not completely in memory. It means that a part of process is in the memory and part of it is not in the main memory but maybe on the disk, secondary storage. So what is the advantage of virtual memory? It means that those programs can be executed which are larger than physical memory. Like if you do not have enough memory to load entire process into the main memory for execution, you can still execute that process by keeping the part of that process into a hard disk or in a virtual memory, because virtual memory is like it is not in the main memory but on hard disk. So it provide us a view that is an abstract view which separate user logical memory from physical memory. And when we separate the logical memory from the physical memory, it allow an extremely large virtual memory to be provided for programmer when only a small physical memory is available. Like you don't have enough physical memory available, but you have a large enough virtual memory available for you, and programmer can still execute their program. So the programmer no longer need to worry about the amount of physical memory available, and they can concentrate on the programming problem that has to be solved. So in case of using virtual memory, a program would no longer be constrained by the amount of physical memory that is available, and each program could take less physical memory, so more programs could be run at the same time, and less IO would be needed to load or swap portion of program into memory, so each program would run faster. So it will also allow for more efficient process creation. In this chapter we will discuss how to implement virtual memory. So virtual memory can be implemented using two schemes. One is demand paging, another one is demand segmentation. So here in this figure we show that how the logical memory is separated from the physical memory. As you can see that we have here virtual memory and we have a memory map, and this memory map is used to map the pages that are stored on in virtual memory to the physical memory, actual physical memory. Okay, this figure show the virtual address space. Now what is a virtual address space of a process? It is a logical view of how a process is stored in memory. So when we look at this view, a process begin at a certain logical address. Like for example, you can see over here that we say that program start at logical address 0 and it exists in contiguous memory, like 0 to max. So when we look at the logical or virtual address space, we perceived it that our whole program is allocated as a contiguous memory in logical address space or virtual address space, but actually when we map it into the main memory, it is not contiguous. You have already seen it in the previous chapter. Here in this figure you can see that the heap size is not fixed. It can grow and in upward direction because it is used for dynamic memory allocation. Dynamic memory allocation mean we allocate memory only when it is required. Okay, and we allow stack to grow downward. Like you can see here, stack is growing downward, And if you look here in between this stack and heap, you will see a large blank space, or you can say a hole, and this hole is part of the virtual address space, but it will require actual physical pages only if the heap or stack grows, that is dynamic memory allocation. And this kind of the hole, it is called sparse address space. So if virtual address space include holes like we have shown over here, then this hole is called sparse address space. And if we are using a sparse address space, it is good because the holes can be filled as the stack or heap segment grow, or if we wish to dynamically link libraries during the program execution time. Here in this diagram we show that as we know that logical memory is separated from physical memory. So virtual memory, another benefit of it is that it provide us files and memories to be shared by two or more processes through the page sharing mechanism. Like we have already seen in the previous chapter that we have only a one copy of shared pages that are present actually in the physical memory, but these pages can be shared by multiple processes in their logical address space. Like in logical address space, if these two processes are there, they have this shared library available in their logical address space, but in the middle we shown over here the actual main memory. In the main memory only one copy of these shared pages exist, which is being shared by both the processes. So this can be used to shared system libraries, like standard C libraries can be shared by many processes through mapping of shared object into which virtual address space, or similarly these shared pages scheme can be used for memory sharing scheme that can be used for process communication, that we have already seen in chapter 3, inter-process communication using shared memory. And pages can also be shared during a process creation with fork system call. Okay, in the demand paging scheme, the basic idea is instead of loading the entire program into memory, you only load those pages into the memory which are required. Like let's suppose we have a program which have a list of different options available, and user have to select some options out of it. So loading the complete program into memory results in loading the executable code for all the option. There are maybe some options that are never selected by the user. So loading the code for that option into memory is just wastage of the main memory. So in demand paging, what we do is we load pages only as they are needed. So the benefit of demand paging is that first thing, less input output is needed because you will only input or out those pages which are required. Less memory will be needed because those code part or those pages which are not being used will never be loaded into memory and provide faster response, and you can use memory efficiently by entertaining more number of users. Okay, there is one thing that is called a lazy swapper. What is a lazy swapper? It means never swap a page into memory unless page will be needed. So demand paging is more like the paging scheme with swapping, like swap in, swap out. So the swapper that deals with paging is called pager. Okay, what is this invalid reference and not in memory? This is what we are going to discuss now in this coming slide. Okay, here we just show that we keep all the pages onto hard disk and we swap in only those pages which are required during execution, and then swap out some other pages into backing store or your hard disk. This shows your backing store that we already discussed with paging with swapping. Okay, as we know that the basic idea behind demand paging is to load a page in memory only when it is needed. So it is possible that when a process is executing, some pages will be in memory and some will be in the secondary storage. Thus we need some form of hardware support which tells us that when a page is, whether this page is already present in a memory or it is on a hard disk. So for this purpose we can use, like we have already seen in paging, we maintain a page table, and page table, with page table we have valid invalid bit with each entry. So this valid invalid bit can be used to tell us that whether a page is already in memory or on a virtual memory or in a backing store. So with demand paging, this page table can work with this valid invalid bit. If bit is valid, it means page is in main memory. If this bit is invalid, it means page is on a virtual memory. Like in the previous chapter, this valid invalid bit is interpreted in a different way. Valid mean this page belong to the memory space of this process, and invalid mean this page does not belong to the logical memory space of this process. Like this valid invalid bit was being used in paging for process protection, but here we are using it in demand paging to distinguish between this thing, that whether a page is present in memory or it is on a virtual memory. So if it is in a main memory, bit will be valid. If it is invalid, it means the page is in the virtual memory. So if the bit is invalid and page is not present in the main memory, so it cause a phenomena which is called page fault. Page fault mean page is not present in the main memory, it is on a virtual memory. So we need to bring that page into main memory. Okay, if we look into this example, this is the logical memory, this is corresponding physical memory, and this is the page table. And now if you look at the physical memory, and this is the backing store. So backing store or virtual memory hold all the pages of this process from A to H. But physical memory currently hold only 3 pages, which is page number 0, that is A is page number 0, C is page number 2, and F is page number 5. So if you look at the page table, you will see 0, 2 and 5. Only these 3 entries are valid and corresponding frame numbers are there. But all the rest of the pages are not in the virtual in the main memory currently. So the corresponding bit is invalid for them. So if it is invalid, it means that these pages are in the virtual memory and we need to bring them into main memory. And if some reference occur to the pages which are not in the virtual memory, then it causes page fault, like we have seen over here, this thing, page fault. Okay, so we have already known that what is a page fault. So how to handle this page fault? If this page fault occur, what are the steps that operating system need to take? So for this purpose, operating system first need to look at an internal table to find out okay, what is this internal table? It is usually kept with the process control block, and first what we do is that operating system will check an internal table for this process to determine whether the reference was valid or invalid memory access. Okay, if because you know when bit is invalid, if it is a valid, page is in main memory. But if it is invalid, there are 2 cases. If it is an invalid, there can be 2 possibilities. One is page is not present in main memory, it is in a virtual memory. But the second option is, if it is invalid, the other reason can be that this reference does not belong to the logical address space of this process. It means that this process want to access the memory of some other process. So first, operating system look into the internal table and find out whether the reference was a valid or invalid memory access. So if it is an invalid memory access, then operating system terminate the process. But if it is valid, so what we have to do is that a page need to be bring into the main memory. So for this, they have to find an empty frame and then have to bring the page into main memory. Like here, the whole process is shown. So whenever a reference is made by the CPU for any instruction like load M, so it has to look where is this M in the main memory. So in order to check where is this M instruction is present in the main memory, first step is it will go and check into the page table. When it go and check into the page table, it find out that the corresponding entry is invalid. So if it is invalid, a trap will be generated and control will go to the operating system. So operating system will go and check into the internal table and find out whether this reference is valid or invalid. Like if this bit is invalid, then further it has two options. If it is an invalid memory reference, operating system will just terminate the process. But if it is a valid memory reference but the page is not present in the main memory, so what it has to do is it will go and look for that page in the backing store and then bring that page into the main memory and then load the address of this frame into the page table and then restart this instruction. Okay, like in case of TLB, when we add TLB in paging to increase the efficiency, so same here when we are looking at the effective access time or performance of demand paging. So they said that page fault rate lie between 0, probability of page fault lie between 0 and 1. If P is equals to 0, it means page fault never occur, and whenever CPU needs some frame is already present in the main memory. And if P is equals to 1, it means every reference is a fault. So whenever CPU wants to look for some page, that page is not in main memory and it has to bring from backing store into main memory. So in order to bring a page from backing store into main memory, update the page table and all that, it takes time, it adds delay. So what will be the effective access time in case of demand paging? So how can we calculate this? We can calculate it by 1 minus P into memory access plus P. P is what? Probability of page fault rate, and 1 minus P, that page is present in the main memory. So if it is present in the main memory, you just go directly to the main memory and access it. And P mean probability of page fault, it mean page is not present in the main memory. So we have to go for first page fault overhead, that is the time taken by operating system to go and check whether this memory reference is valid or not, and then swap one page out, swap page in, and then restart overhead. So all these things will add some time. And what will be the effective access time? It mostly depends on the probability of page fault rate. So if page fault rate is high, this effective access time will be more. If a probability of page fault is less, then effective access time will be very less. So here in this slide, there is just an example, like if memory access take 200 nanosecond, and if there is a page fault occur, and in order to service that page fault service time mean all the time it takes to do these all steps: page fault overhead, swap page out, in, restart overhead. So all these things, if it takes 8 milliseconds, so what will be the effective access time? So effective access time will be can be calculated by using the same formula that we have discussed in the previous slide, and it would be like this much. So if we say that the probability of page fault is 1 access out of 1000, so 0.0001, then effective access time will be 8.2 microsecond, and this is slowed down by a factor of 40. So how we get it factor of 40? Because if we directly access memory, like it will be 200 nanosecond multiplied by 1 minus P, but if we are going to go through page fault, it will be 8.2 microseconds. So it just slow down. So you can see here that P is 0.001, 1 minus P is 0.999. So effective access time in case of page fault probability this much is 8.2 microsecond. So how they got this 40? 8.2 microsecond divided by 200 nanoseconds, so it gives you approximately 40%, factor of 40. Yani it is it slow down this much if we are going to keep demand paging. Like if we are keeping all the data into main memory, we can access in 200 nanosecond, but in case if we are doing demand paging, the same thing will be done in 8.2 microseconds, so slow down by factor of 40. And how this 40 we got 8.2 into 1000, that is microsecond, divided by 200, so you will get this 40 value. Okay, we know that we create a process using fork system call. So when we use this fork system call, it creates a child process, and that child process is the duplicate of its parent. So fork work by creating a copy of the parent address space for the child. So it will duplicate all the pages that belong to the parent. So if we consider that many child process will call execute system call immediately after creation, so the copying of parent address space may be unnecessary. We don't need to make the copy of the parent, because when child call exec system call, it is executing its own new program into it. So for this purpose we use a technique known as copy on write. So how copy on write work? It allows the parent and child process initially to share the same pages, and then these pages, shared pages, they are marked as copy on write pages. What it means by copy on write? It means that if any of the process, whether parent or a child, write to a shared page, a copy of the shared page is created. Like here you can see in this example, we have two processes, process 1 and process 2. Maybe these are parent and child process, and in the physical memory these both processes are sharing a same copy of page A, B and C. Okay, now let's suppose process 1 wants to make some changes into the page C. It's a child process, and this child process, what we do is we create a new copy of page C, and process 1 can make changes to this copy. But if they are not making changes to these pages, then there is no need to duplicate these pages into physical memory. So it is same like that we have already discussed in the previous slide, is sharing the memory pages. So in physical memory we keep only one copy of these pages, and these parent and child processes are sharing those processes. And whenever some process wants to make change into any of the process, a copy of that page can be created, and that can be updated by that process. And this scheme is called copy on write. Okay, when a process is executing and if a page fault occur, then operating system has to find out where the desired page is present on the secondary storage, but then find that there are no free frames in the main memory on the free frame list to bring that page into the main memory. So then what have to do? So in that case we need some page replacement algorithm which will find some free page or some free frame in main memory that is not really in use. And if if there is no space available in the main memory, or there is no free frame available in the main memory, and you have to bring one page from backing store to the main memory, then we need some algorithm which has to perform this page replacement. So and we have to find out the algorithm which will have a good or optimal performance, and we need a algorithm which will result in minimum number of page fault. So same page may be brought into memory more than one time. Okay, now in this example consider the situation that there is two processes. One is process 1. Here we show the process 1 logical memory and process 2 logical memory, and here we have a physical memory. Now if you look here that your CPU generate access for page B. So when we look into the page table for page B, we find out that it is page number 1, and corresponding entry is invalid. So if it is invalid and we find out it is a valid memory reference, but this page is not present in the main memory, so what happened? Page fault occur. So when page fault occur, we know that what we have to do is we have to load this page from the backing store into the main memory. But when we come back to the main physical memory, we can see over here there is no free frame available to bring this B into the main memory. So now what to do? So here there is a problem that we need to solve, and this problem is solved with page replacement algorithm. We need to know, look for different page replacement algorithm which help us to find a free frame. If there is a free frame, okay, there is no problem. We can bring B from backing store into the physical memory. But if there is no free frame available in main memory, then we have to make a space. We have to replace some page from physical memory. We have to send some data, some pages from physical memory into the backing store, and so that we can bring B into the physical memory. So now what is the basic algorithm that is being followed in that case? So look here, what we have to do is we have to find the location of desired page on disk. Like here we find out that where is this B located on the backing store. So we find out B is located on this place. Okay, the second step is we have to find a free frame. If there is a free frame, we can use it, but we have seen in this situation there is no free frame in physical memory. So now what is the else condition? If there is no free frame, then we have to use a page replacement algorithm to select a victim frame. Now what is a victim frame? Victim frame over here is the frame which you choose to take it back or swap that page out onto the backing store. Okay, you have to swap out a page into the backing store so that you can make a space for a page that is on backing store to bring it into main memory. So swap out victim onto the backing store and swap in the desired page on the place of the victim frame. Once it has been done, then what you have to do is you have to make change over here into the page table, because you bring that page back into the main memory for F, so your invalid bit will be reset to valid. You have to change it to valid, and that frame, like here if we replace frame O, so O will become invalid and F become valid, and then reset page table for this new page. So once you select the victim page, at that time you have to change page table, and when you swap in the desired page, then you have to change again the page table. So for victim, you will change valid invalid bit to invalid, and when you bring the desired page, for that page you will change from invalid to valid. So you will see you have to make changes into the two entries of the page table, one for the victim and one for the desired page. O is the victim, previously it was valid, after swap out we make it invalid, and after swapping in F, previously it was invalid but now it become valid. Okay, you might have noticed over here that if there are no free frames available, then we have to transfer two pages. One is to victim to the backing store, another one is from backing store to the main memory, and this situation doubles the page fault service time and increase the effective access time as well. So what we can do to solve this problem is we can reduce this by using a modify or a dirty bit. When this scheme is used, each page or frame has a modify or dirty bit we attach with each page, this bit as well in the hardware. Like you have valid invalid bit, so same is modify or dirty bit that you attach with each page in the hardware, and this modify bit for a page is set by the hardware whenever any byte in the page is written into, so it shows that the page has been modified. So when we select a victim page for replacement, we examine its modify bit. So if the modify bit is set, then it means that page has been changed or modified. So in that case we must have to write this page back into the backing store. But if the modify bit is not set, it means page has not modified while it is in the physical memory. So we don't need to replace this page back into the backing store, because every page, one copy is present on the backing store as well. And we know that this page replacement is a basic thing that we have to do when we are performing demand paging, and it completely separate the logical memory and physical memory. So if we are using this page replacement with demand paging, so you can have a large virtual memory on a smaller physical memory, and you can effectively use it. Okay, so when we are using demand paging, we have to solve two major problems. One is a frame allocation algorithm, and the other one is page replacement algorithm. Frame allocation algorithm means that if we have multiple processes in memory, so we must have to decide how many frames to allocate to each process. Yani each process might have 100 pages, and in physical memory we have only limited number of frames available. So we have to decide out of these 100 pages per process, how many pages need to bring into the main memory. First thing, which is a frame allocation algorithm, and the second thing is page replacement algorithm. Like we must select the frame that are to be replaced. So page replacement algorithm mean when we must have to select the frames that need to be replaced from main memory to virtual memory, and virtual memory to main memory. So when we are designing an appropriate algorithm to solve these problems, it is very important to look for an optimal algorithm, because we know that bringing data to the secondary storage and swapping in and swapping out, this is an expensive operation. So we want some algorithm which provide us lowest page fault rate, because when you have less page fault rate, it means you have to bring less number of pages from secondary storage to the main memory. So we will look for that algorithm which give us lowest page fault rate. That algorithm will be the optimal algorithm. So when we are evaluating the performance of algorithm, we evaluate it by running on a particular string of memory references, and then we calculate the number of page fault on that string, and the algorithm which gives us minimum number of page fault will be considered as optimal algorithm. Okay, this graph shows the performance of page fault versus the number of frames, and it is obvious, if you have more number of frames, then number of page fault will automatically reduce, so and performance will be increased. Okay, now we will discuss different page replacement algorithms. So the first one is first in first out algorithm, and we consider this reference string. Now what is this reference string? We can generate this reference string artificially, like we can use a random number generator, and we can generate some number randomly, or you can trace a given system and record the address of each memory reference and use that record as your reference string. So these reference strings are basically used to compute the performance of algorithm by calculating the number of page faults. Okay, now we will start with first in first out, like here if you can see. Okay, in this example, upper part we assume that we have 3 frames available in the main memory, and initially all 3 frames are empty. So first if we look at this reference string, this is our reference string. So we will bring these pages one by one into the free frames. So for each free frame, one page fault will occur. So when you bring 1 into the main memory, 1 page fault. Then you bring 2 into the main memory, second page fault. Then you bring 3 into the main memory, third page fault. Okay, and after that there is no space available in the memory, and now we need to bring page number 4 into the main memory, and memory is already full. and this scheme work on the principle of first in first out. So which page we bring first into the memory? This one. So what we have to do is we will take 1 out and bring 4 into the main memory. So another page fault. Okay, after that we need again 1, so we just bring 1 into the take it out, we need to bring it again. So first in first out, so now 2 will be removed from the memory and 1 will bring into the memory. Okay, and then we need 2. So what we have to do is 2 is not present over there, so first in first out, so 3 will be replaced from the memory and 2 will bring into the memory. Okay, and after that we need to bring 5. 5 is not present in the memory, so again it will work on the first in first out, so 4 will be moved out and 5 will be bring in to the main memory. Okay, now 1 is required and 1 is already present in the memory, so there is no page fault for it. Then 2 is required, 2 is already there in the memory, there is no page fault for it. Okay, then 3 is needed and 3 is not present here. So currently what we have in the frames 5 1 3, so we need to 5 1 and 2, we need to bring 3. So first in first out, so 1 will be removed and 3 will bring on its place. Okay, right now what we have in the memory 5 3 4. Okay, we need to access 4. 4 is not there, so first in first out, 2 will be moved out and 4 will bring into main memory, and then in the end we need 5 and 5 is already present in the main memory. So now what we have to do is we have to calculate how many page fault occur. So if we look here, 1 2 3 4 5 6 7 8 9, 9 page fault occur in this case on this reference string when we have 3 frames available. Okay, now what we will do is we will look at the performance of the same algorithm on same reference string, but we increase the number of frames from 3 to 4. Okay, so when we look into it, okay, I will just delete it first. Initially all 4 frames are free, so we bring 1 2 3 4 into the main memory, so 4 page fault already occur at this time. Okay, now after that, okay, until here we already bring with 4 page faults. Okay, and then we have to access 1 is already present there, so we don't have any page fault for 1. Okay, we need 2 is already present over there, so there is no page fault for 2. Okay, now we need 5 and 5 is not present over here, so we need to bring it into the main memory. So first in first out, so 1 will go out and 5 will bring into the main memory, so 1 page fault here. Okay, then after 5 we need 1 and now 1 is not present in the memory, so we have to bring it, so 2 will move out and 1 will bring into the memory. Okay, after that we need 2 and 2 is not present in the memory, so what we have to do is we have to remove 3 and bring 2 into the main memory. Then we need 3, so 3 is not over there, we have to remove 4 and bring 3 into main memory, and after that we need 4. So again first in first out, 5 will move out and 4 will bring in, and in the end we need 5. So in order to bring 5 we have to take out 1 and have to bring 5 into memory. So now in this case if you look here, instead of 9, although we increase the number of frames, but the number of page fault also increase, so now it is 10 page fault instead of 9. Although we have seen previously in this graph that if we increase the number of frames, number of page fault should be decreased, but here in this special case this thing is not happening. So sometimes this phenomena occur, and this is called Balady's anomaly. And what is this Balady's anomaly? Balady's anomaly is stated like, if we have more frames, then sometimes, because this is anomaly, this is a situation that unexpectedly occur, you have more page fault. So if the such situation occur, it is called Balady's anomaly. So if we consider this Balady's anomaly, then this graph is not like this. it will be changed over here. Like if you increase the number of frames, sometime page fault increase, like when we move from 3 to 4, so number of page fault for 3 will be 2, but when we increase it to 4, it goes to 10. Okay, here in this slide we have another example on first in first out page replacement with the different reference string. Like this is the reference string and this is our page of frames. So initially we assume all 3 frames are empty. So first page fault occur for 7 will bring into memory, then for 0, so 0 will bring into memory, then for 1, so 1 will bring into memory, and now our main memory is full. So after that we have to go for page replacement. So when 2 is needed, 2 is not present into the main memory, we need to bring over here into the main memory. So we have to replace 7 with 2. So 7 will be move out and 2 will bring into memory, and this is how our main memory look like. Now memory consists of 2, 0, 1. So this is page fault. I'm just ticking page faults so that we can count them later on. So these are 4 page fault until now. Okay, next is 0, and 0 is present in the main memory, so there is no page fault for 0. Okay, next 3. So currently memory is 201, so we need a replacement. So first in first out. So 7 already has been replaced, so the most recent now has to replace it with 0. So 0 will be replaced and 3 will bring into memory. So this will be page fault. Okay, now memory look like this, 2, 3, 1, and we need 0. 0 is not present over here, so we need to bring it into main memory. So first in first out. So 1 will be moved out and 0 will bring into main memory, and this is what? A page fault. Okay, now we need 4 and our memory look like this, 2, 3, 0. So we have to bring 4 into memory. So again first in first out. So 2 will move out and 4 will bring into main memory. Okay, 4, 3, 0. This is how our main memory look like now, and we now need 2. 2 is not present over here, so what we have to do is we have to look for some victim. The victim is 3. Okay, page fault occur and 2 will bring in. Next we need 3. Again 3 is not present over here, we need a victim. So victim is now 0 and 3 will bring over here. Okay, so this is a page fault. Now we need 0. So 0 is not here, so we have to bring in. So 4 is a victim and 0 will bring on its space, and this is page fault. Okay, now our memory look like this, 0, 2, 3. We need 3, 3 is already present. We need 2, 2 is already present. Now we need 1. So 1 is not present and we need to bring it. So what will be the victim now? 2 is the victim and 1 will bring into main memory. Then we need 2. So 2 is not present over here. We have to bring it. Victim is 3 and 2 will be placed over here. So it look like this, 0, 1, 2. Okay, 0. We need 0. 0 is already there. We need 1. 1 is already there. Okay, now we need 7. 7 is not there. We have to bring it. So we need to choose a victim. Victim is 0 and 7 will place over here in the place of 0. So this is our page fault. And then we need 0. So 0 is not here. Again we have to bring it. Victim is 1 and 0 will bring in the place of 1. Okay, and this is page fault. And in the end we need again 1. So we have to again has to choose a victim. Victim is 2 and we bring 1, and this is page fault. So now we can calculate how many page fault occur. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 page fault occur in case of this reference string with first in first out. So they said that first in first out is not considered to be an optimal algorithm because of this Balladay's anomaly. So we can look for some other algorithm, good algorithm for page replacement. Okay, then the other algorithm that is used for page replacement is called optimal algorithm. And why we called it optimal algorithm? Because it is known as the best algorithm that is used for page replacement, because its performance is best in term of it gives us minimum page fault. So what is the idea behind optimal algorithm is that it replaces page that will not be used for longest period of time. Now what it means is we just go and look into the future, okay, like shortest remaining time first scheduling algorithm. We go and predict already what will be the next CPU burst time. So same over here is in this optimal algorithm. When you have a reference string, you just go and look into the future which reference will not be used for longest period of time, and you choose that page as a victim for replacement. Like if we look here into the example, we have 4 frames in the memory, and this is our reference string. Okay, so initially we have to put all these frames one by one into the memory. So we have 4 page fault. We place 1, then we place 2, then 3, and then 4. Okay, until here. Now we need 1, and 1 is already there, so we don't need to choose for any victim. Then we need 2 is already there, so we don't need to choose any victim. Okay, at this point now, here page fault occur. Why page fault occur? Because 5 is not present in the main memory, and now we have to bring 5 into the memory, and we have to choose 1 as a victim. Okay, now which out of 1, 2, 3, 4 we will choose as a victim? For this we will look into the future. What will be the future references? Okay, so when we look after 5, 1 we need immediately after 5, so 1 is not a good victim. 2, okay, after that 3, after that, and 4. So if we look into this timeline which frames we need in the future, we come to know that 4 is the frame that will not be used for longest period of time. So we will choose 4 as a victim, and 5 will be added in the place of 4. Okay, now after that we need 1, then we need 2, we need 3, all are present over here, and after that we need 4, and 4 is not present in the memory, so we need to bring it into the memory. So if we look here, so 5 we need immediately after that. So we see, like we scan again 1. Okay, 1 we don't need it in the future because here our reference string will finish. So we will choose 1 as a victim, and we will bring 4 over here in the place of 1. So now if you count the number of page fault, first these 4 page faults, and then 1 page fault for 5, and 1 page fault for 4. So with optimal algorithm we have only 6 page faults with the same string. But the problem with this is, how do you know this, that which frames will not be used for longest period of time? You cannot know this until CPU generates the reference to the page. You cannot know that what will CPU generate in the future. So they said that optimal algorithm gives us best performance, but it is practically not usable. So this optimal algorithm is used as a standard. Whenever a new replacement algorithm is being proposed, its performance is measured against optimal algorithm, and if its performance is near to optimal algorithm, then we can say that this algorithm is performing good. Okay, here we have another example for optimal page replacement, the same that we have used previously for first in first out. So now we will go through it for optimal. Okay, so initially all frames are free, and we have total 3 frames. So we will save 7, and then 0, and then 1. So if we go through it, so until this time 3 page faults occur, 1 for 7, 1 for 0, and 1 for 1, and we bring these pages into the main memory. After that we need 2, and 2 is not present over here, so we have to choose a victim. So now how we will choose victim? We will see that when 7 is used after this, if 7 is a victim, so if we scan from here, 7 will be used at this point. Okay, when 0 will be used, 0 will be used at this point in future, and when 1 will be used, 1 will be used over here at this point in the future. So which is the victim, most appropriate victim, which is the frame which has not been used for longest period of time, that is far in this timeline. So 7 is the frame which will not be used for longest period of time. So 7 is the most appropriate victim. So we choose 7 as a victim and we will bring 2 in place of 7. Okay, so 2, this is our page fault. Then we need 0 is already there. Then we need 3. Okay, at this point 3 is not in the main memory. So again we have to choose victim. So now how will we choose victim? I'll just change the color if possible. Or okay. So for 3, okay, 2. When is 2 needed in the future? 2 is needed in the future over here. If we choose 2 as a victim, so 2 is needed here. 0 is needed over here. And when 1 is needed, 1 is needed over here. So out of 0, 2 and 1, which is the frame which has not been used for longest period of time? The one that is farthest on this timeline, that is 1. So out of 2, 0, 1, 2, 0, 1, which should be the victim? 1 should be the victim frame. So we choose 1 as a victim and we bring 3 on the place of 1. Okay, this is our page fault. Okay, then we need 0 is already there. Okay, then we need 4 is not present here in the memory. In the memory currently we have 2, 0 and 3, so we have to choose 1 as a victim. So what is the process for victim? Okay, 2. When 2 is needed, 2 is needed over here. When 0 is needed, 0 is needed over here. And when 3 is needed, 3 is needed at, 3 is needed over here. So 2, 3, 0. So here, which is the farthest on this timeline? 2, 3, 0. 0 is right now farthest, if you see over here. So we choose 0 as a victim and 4 will be placed, or 4 will bring in the place of 0. Okay, then 2 is needed, 2 is already there. 3 is needed, 3 is already there. Now we need 0 and 0 is not here. Okay, so again we have to choose victim. Okay, we will see when 2 is needed, 2 is needed at this point. Okay, when 3 is needed, 3 is needed at this point. Okay, 2 and 3. And when 4 is needed, 4 is not needed in the future. It is not over there. So 4 is the most appropriate victim. So we will place 0 in the place of 4. We bring 0 from in the place of 4. Okay, now 3 is needed, 3 is already there. 2 is needed, 2 is already there. Now 1 is needed and 1 is not in the memory. Memory currently has 2, 0, 3. So which should be the most appropriate victim? So we will do same thing. When 2 is needed, we have to look at this side. Okay, wherever page fault occur, we look at this side. 2 is needed here. Okay, when 0 is needed, 0 is needed over here. And when 3 is needed, 3 is not needed in the future. So 3 is the most appropriate victim. So we choose 3 as a victim and we will bring 1 on the place of 3. Okay, now 2 is needed, 2 is already there. 0 is needed, 0 is already there. 1 is needed, 1 is already there. And now we need 7, and 7 is again a page fault. So okay, now when 7 is a page fault, so how can we bring 7 into memory? Again we will go for the same thing and we will look whether 2 is needed in the future. Now we will go and look here. We have only 2 frames left, only 2 references in the future. So 2 is not needed in the future. So 2 is the most appropriate victim and 7 will bring on the place of 2. And after that 0 is needed, 0 is there. 1 is needed, 1 is there. Now if we count the page fault, you will see 1, 2, 3, 4, 5, 6, 7, 8, 9. So in the same string we have only 9 page fault, and you can compare it with the performance of first in first out, which require more than 9 page faults. So, and because this is optimal, so optimal gave us minimum page fault, but optimal algorithm is not practically usable. Why? Because we cannot predict which pages will be referenced in the future. Okay, the third page replacement algorithm that is used is called least recently used algorithm. So least recently used algorithm will choose that page or frame as a victim which is being least recently used in the near past. So past, you can go and see what has happened in the past. So this is practically possible. So if we go through the example, like this is our reference string and we have 4 frames in the main memory. Initially all frames are empty, so what we have to do is we have to bring 1, 2, 3 and 4 into memory like this. Okay, so we have 4 page faults and all 4 frames have been loaded into memory. After that, 1 is needed, 1 is already present in the memory. Then 2 is needed, 2 is already present in the memory. Okay, now we need 5 and 5 is not here. If you look into this, first box, we have what? 1, 2, 3, 4. So we have to choose victim. Now how to choose victim? We will go this side. Like in the previous, we go into the future. Now we will go into the past and see which frame has been used. Okay. 1 is being used at this point in time in the future. 2 immediately before 5. Okay. 3 is used at this point and 4 at this point. So which is the farthest on this timeline? 3 is the one that least recently used in the past. So 3 is the most appropriate victim. So now we go into this side and see farthest on the line, the page on this side. So 3 is the most appropriate one. So 3 will be chosen as victim and 5 will be loaded in the place of 3. And this is how our memory now look like. Okay, this was page fault. Then we need 1 is already present in the memory. We need 2 is already present in the memory. Now we need 3 and 3 is no more there in the memory. So here page fault occur and we have to go back and see which page we will choose as a victim. So when we go back, 1. So when 1 we use over here, 2 we use over here. Okay, 5 we use over here and 4 is used over here. So 2, 1, 5, 4. 4 is the farthest on the line that is being recently used. So 4 is the most appropriate victim. So we will choose 4 as a victim and 3 will bring on the place of 4. Okay. Then we need 4 and 4 we just replace. So again page fault occur. When page fault occur again, now our memory look like this third side. Okay, we have 1, 2, 5, 3. So 2 here, 1 here, 5 here and 3 over here. So 3 is farthest on the line. 3 is not on the farthest on the line. Page fault occur for 4. So 3 we used over here. Okay, let me just take. If we go back here from 4, 3 is being used at this time. Okay, 2 at this time, 1 at this time and 5 at this time. So 5 is the one that is farthest on the line right now. So 5 will be chosen as a victim and 4 will be loaded at the place of 5. Okay, and then we need 5. So now again this is a page fault and we have to choose a victim frame. So go back. Now this is how our main memory look like. So 1 is used over here, 2 is over here, 4 is over here and 3 is over here. So which out of these 1, 2, 3, 4, which is the farthest on line? 1 is farthest on the line. So we will choose 1 as a victim and 5 will be placed in the place of 1. Okay, and this our reference string finish. So how many total page fault occur? 1, 2, 3, 4, 5, 6, 7, 8. 8 page faults occur in this reference string when we use least recently used algorithm. And if we compare it with optimal, because same thing we use with optimal and we have 6 page fault. So least recently used is better than first in first out because first in first out has more page fault and it is near to the optimal algorithm. Okay, when we are implementing least recently used algorithm, we can implement it with the help of counter. So they said that every page entry is associated with a counter, and every time when a page is referenced through this entry, copy the clock into the counter, and when page need to be changed, look at the counter to determine which are to change. Like you look at the counter for all the pages that have been referenced into the past, and the one which is having least value for the counter, we replace that page. Okay, now this is another example, the same example that we have already run on optimal algorithm and first in first out. Now we will run it on least recently used algorithm. So this is our reference string, and we have 3 frames in the memory. Initially all 3 are empty, so first time 7 will be loaded into memory, so 1 page fault, then 0, and then 1, so 3 page fault will occur at this point until here. Okay, we are here. Now 2 is needed, so we have to look for the one victim. 2 is not present in the memory, so we go back into the past and see least recently used. So 1 is over here, 0 is over here, and 7 is over here. So 7 is the farthest on this line in the past, so 7 will be the most appropriate victim. So we choose 7 as a victim, and we will load 2 in place of 7. Okay, then we need 0. 0 is already over here. Then we need 3, and 3 is not present in the memory, so page fault will occur for 3. And now we have to choose victim out of 2, 0, 1. So this is 2, 0, this is 2, and this is 1. If we go back into the past, so which is farthest on this line? 1 is farthest on this line, so it will choose 1 as a victim, and 3 will be placed there in the place of 1. Okay, then we need 0. 0 is already there, but then we need 4, and 4 is not over here, so page fault occur. When page fault occur, again we go back into the time, and we see 0 we just recently use over here, 3 we use over here, and 2 we use over here. So 2 is farthest on this line, 0, 3, and 2. So 2 will be chosen as a victim, and 4 will be placed in the place of 2. Okay, now our main memory look like this, 403, and we need 2, and 2 is not over there, so we need again to choose a victim. We need page fault, we need to free a frame. So which page will be chosen as victim? Again we will go into the future, 403. So which is on the farthest in this timeline? 3. So 3 will be chosen as a victim, and 2 will be placed on the place of 3. Okay, now we need 3. So we have to again page fault occur, and we have to bring 3 into the memory. So what we have to do is again 402. So if you look here, 240, so which is farthest on this line? 0. So 0 will be chosen as victim, and 3 will be placed in place of 3. Okay, now we need 0, and we just replace 0. So again we go back here, 432 is in memory, and if we look here, 432, so this 4 is farthest on this line, so 4 will be chosen as victim, and 0 will be placed here. Then we need 3. 3 is already there. We need 2. 2 is already there. We need 1, and 1 is not over here. So again we have to choose victim, and if we look 230, which is farthest? 0. So 0 will be a victim frame, and 1 will be placed in 0. Okay, then we need 2. 2 is already there. Again we need 0, page fault occur, and we have to bring 0. So again we have to choose victim. So 2 is over here, 1 is over here, and 3 is over here. So 3 is farthest on this line, so 3 will be chosen as victim, and 0 will be placed on 3. Okay, and this is how our main memory look like. Now we need 1. 1 is there. We need 7. Page fault occur. 7 is not here, so again we will go back here and see which is the victim. 1, 0, and 2. 2 is the victim, so 7 will placed on 2. Okay, and after that 0 is needed. 0 is there. 1 is needed. 1 is there. So if we count total number of page fault, we will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 page fault. And if we compare it with optimal have for the same reference string, 9 page fault, but FIFO have more than 17 or 18 page fault. So least recently used algorithm is having a better performance as compared to first in first out with the same string when we compare and near to the optimal. Okay, here in the last slide we have just given an example for you to practice. Just consider this reference string and see how many page fault occur in case of LRU, FIFO and optimal replacement algorithm if we have a demand paging with 3 frames, and find out the answer. So this is just an practice that you can do by yourself. And here we finish our virtual memory chapter. Thank you.